Okay, today we're going to be working in section P.1 or P.1, chapter P, the preparatory chapter, section 1. And this is a lot of, again, it's review material, it's stuff that you should have a grasp of. But we're going to get into some of the stuff maybe a little deeper than we have in the past. That's part of what college algebra is about. First thing we want to learn about is real numbers, and what do we mean by real numbers, and what's included in all of those. Really what we're going to do is we're going to exclude the imaginary numbers. If you remember from Algebra 2, square roots of negative numbers, those were our non-real numbers, or our imaginary numbers. But real numbers really encompasses so many different types of numbers, and you might at first think, why do I need to classify them in special ways? But we classify them in special ways because the way we group them, the way that they interact, we want to know, are there patterns that are constant for different types of numbers, and also are certain types of numbers better for describing data or for encryption, security, different things. So there's a lot of applications for different types of numbers. So we classify them. The most basic type of number is your natural numbers. And you can think of the natural numbers as what you would count. If you pulled out your fingers and started counting, you'd start at 1 and you'd count your way up. So natural numbers are numbers that are the counting numbers, starting from 1 and going up infinitely outward in the positive direction, always adding one more. Whole numbers is when we start to extend that just a little tiny bit, and by a little tiny bit I mean the only thing we actually include extra is the number 0. See, 0 is not a natural number because it's not a counting number, but it is part of what we call the whole number family. Okay? If we go a little bit further, because it's possible to have 0 of something, and so to the ancient people, 0 or 1 or 3 of something made sense. But eventually the concept of negative numbers were developed, where you actually owed something, or there was less than 0 of something. And so integers, they include the natural numbers. That's why it's inside that circle. It includes the number 0, but it also includes the negative whole numbers. So, or negative natural numbers. So if we take all these numbers, see how the circle keeps getting bigger? We're still including those other numbers. So the number 2, it's a natural number, it's a whole number, and it's also an integer. And so we continue to expand those things outward. The next group, as we continue to expand that out, is what we call rational numbers. Now all of the stuff that lives inside of that box is a rational number. So natural numbers, whole numbers, integers, they're all rational numbers. Rational numbers are really the first thing that really needs to be explained. Okay, rational numbers are anything that can be written as a fraction. Okay, so we need to be able to write it as a fraction so that the top is an integer and the bottom is an integer. Okay, they can't be decimals. You can't put 2.3 over 5.789. They have to actually be integers that are on top and bottom. Now you might say, but Mr. Welch, negative 0.75 is not a rational, or it's not a fraction, right? Well, I could write it as negative 3 over 4. Now we can see that this is a rational number. So when we talk about rational numbers, the question is, can it be written as a fraction? Typically anything with a repeating bar, that can be written as a fraction. But what can't be written as fractions are what we call irrational numbers. Now, irrational numbers are kind of a catch-all of whatever else exists that doesn't fit these other categories. And so we look for numbers that can't be written as fractions, and typically what that means is that the decimal is non-repeating and that it's continuous. So it would go on forever but never have a pattern of repetition. So numbers like pi, the square root of 10, 7.12510582062 ... There's no pattern there. There's no repetition. Those numbers are irrational. They cannot be written as fractions. We might write fractional equivalents, like oftentimes 22 over 7 is used for pi, but it is rational and it's only an approximation. It's not the actual value of pi. So that's just our classification system. Hopefully you can distinguish the different types of numbers. The next thing we want to talk about is absolute value. And I know you guys have some background with absolute value. You know what it is, but let's just clarify and define. The absolute value of a number is the distance from that point to 0 on a number line. Distances are measured positive. Think about it like a tape measure. Okay? So it can be positive or it can be 0 units from 0. And so the absolute value of -4, well, it is 4 spaces, so it is 4. And the absolute value of +5, it's 5 spaces, so 5. So let's do just some real quick example. We want to simplify a and b, where we're letting x be -3 and y be 7. So this would equal the absolute value of -3 plus 7. Well, we're going to think of the absolute value bars a little like parentheses. When we're simplifying, we have to work inside the parentheses first. And so -3 plus 7 makes this the absolute value of a +4. And the distance from 4 to 0 is 4. Over here we have the absolute value of x, which is -3, minus the absolute value of y, which is 7, or of y being 7. The absolute value of -3 is 3, and we're subtracting the absolute value of 7, which is 7. 3 minus 7 is -4. And there's our answer there. So again, making sure you understand, absolute value bars only affect the equation when everything inside of them is done. For instance here, some people like to try to change this negative. They say, well, it's got to be positive because it's in an absolute value. But the problem is that there's still work to be done before we apply the absolute value. Okay? So make sure that you've done all the math inside before you do the other. If you want to find the distance between two numbers or 2 points on a number line, we're going to do an absolute value, but we're going to do a subtraction absolute value. So for instance, the distance between P and Q is either the absolute value of B minus A or the absolute value of A minus B. The order won't matter between the two numbers. So let's use this pattern to do this both ways. Okay, in this problem, we would want the absolute value of -3 minus 16 or the absolute value of 16 minus -3. Whoops. And we'll put parentheses around that. Okay, so according to the formula up here, it shouldn't matter which way we do it. And so if we come down here and we look real close, -3 minus 16, that's -19, but that's still in the absolute value. And the absolute value of -19 is 19. If we come over here, this double negative here is going to change to a plus, because minus minus is plus, and 16 plus 3 is 19. So I have the absolute value of 19, which is 19. So we can see that it doesn't really matter which order, as long as we make sure we use one minus sign between the numbers, and the numbers have to stay the way they were. So I didn't use this negative to represent the negative in front of the 3. It has to be its own sign. The next thing we want to talk about is just real quickly some of the basic properties. There's 5 of them that we want to make sure we identify. You'll see a little bit of this in your homework. We have what's called the associative property. And if you look at it, associations are kind of like groups, like who you associate with. And if you look, what's changed here is that B and C were hanging out together, but now A and B are hanging out together. But be careful. The order of the numbers, or the order of the letters in this case, didn't change. It was A, B, C. Then it stayed A, B, C. What changed was the grouping, where the parentheses went. And in addition, where it's all addition, or in multiplication, where it's all multiplication, it doesn't matter where the parentheses go. This is the same as saying that if it's strictly addition or multiplication, and you can include subtraction and division, okay, order doesn't matter. So if you think about 2 plus 3 plus 5, sorry about the sloppy handwriting. If I did 2 plus 3 plus 5 and I did the 3 plus 5 first, that's 8. 8 plus 2 is 10. You get 10. Well, what if I do 2 plus 3 first? That's 5 plus 5. That's 10. That's what we're saying. The order in which you do the addition doesn't inherently matter, as long as it's all addition. Now, if there's some multiplication in there, I have a problem. Commutative, if you think about the word commute, commute means to go or to travel, to move. And so the commutative property is when we switch them places. We didn't switch the math, it's still plus, but instead of doing 4 plus 3, we're doing 3 plus 4. Is there a difference? Mathematically, no. And that's what we're trying to prove, is that we can just move things around and it's okay. So commutative property. The next thing is the identity. What that means is that we're not changing the number. So to have what's called the additive identity, it would be to add 0. If you add 0 to something, does it change? No. If you multiply by 1, does something change? No. So that's what we mean by identity. It stays who it is. We have what's called the additive inverse, which means to add the opposite. And we have the multiplicative inverse, which means to multiply by the opposite. Here, when you add something to its opposite, you should get 0. When you multiply by someone's opposite, the multiplicative opposite, you should get 1. So 3 times negative 3 doesn't give us a value of 1. That's because it's an addition inverse. In multiplication, we would need to multiply 3 by 1/3 because that would undo the number, remove the number from itself and give us 1. And last, you have distributive property. Obviously, we know what distributive property is, and we should be able to tell that we're seeing that A times B and A times C over here. Okay. The last thing we need to look at is just simplifying expressions. Okay. When we are simplifying, when the word simplify pops up, we're going to go ahead and use PEMDAS to combine like terms and to simplify. So in this case, we're going to take care of parentheses first. There's nothing we can do in the parentheses, so we're going to distribute. Distribution property right here. 28x minus 21y plus 10x plus 2y. Now we're going to look for all the multiplications done here. Now we're looking for addition and subtraction to simplify. Well, I see 28x plus 10x. Now this plus, I'm applying only to this 10. Don't think of it as plus 10x and it's also plus a positive 2y. Sometimes people think that this is, for everything after we've distributed. A minus, it would get distributed and it would have its own characteristic. But here we got 28 and 10, that's going to be 38x. Then we got a negative 21 and a positive 2. Be careful there. It's minus 19y. Now this is a simplified algebraic expression. Coincidentally, just as a side note, you'll notice this as time goes on. This is not something I would have you do in a traditional class, but some of you might wonder, could I do something to that? There is a process of factoring you could do here, because 38 does divide by 19. If you pull the 19 out by factoring, you'd be left with 2x minus y. Now this looks a little simpler to some people. Other people are going to like the 38x minus 19y. So either one would work. All right, hopefully that's everything you need, and you can come and ask questions when you get stuck. All right, good luck.